All right, today we're diving into a framework that's really shaking up how we build with large language models. It's called DSPy, and it's built on a pretty radical idea. What if we could stop all the guesswork with prompts and actually start programming our LLMs with real logic? Let's dig in and see what that actually looks like.
So, to really get why DSPy is such a big deal, we have to start with the problem it's trying to solve. And honestly, it's a headache that pretty much any developer who's worked with language models has felt.
I mean, have you ever been there? You spend hours, maybe even days, getting a prompt just right. It's perfect. And then the data changes a little bit, or a new model comes out, and the whole thing just breaks. It's this super frustrating cycle of battling these long, brittle strings of text.
Yeah, this old way of doing things feels a lot more like alchemy than engineering, right? You're just tinkering with words, hoping you stumble on the magic spell that makes the model do what you want. And worse, anytime you change anything, the model, your data, how do you even measure success? You're basically back to square one, starting that whole tinkering process all over again.
This right here, this really gets to the core of it. The traditional way is all manual, it's fragile, and you pour all your energy into crafting one giant monster prompt. DSPy just flips that completely on its head. It's modular, it's adaptable, and it lets you focus on the big picture, the actual workflow of your program, while the framework handles all the messy, low-level prompt optimization for you. And that brings us to the fundamental shift DSPy is all about, moving away from the delicate, almost artistic craft of prompt engineering and into the solid, reliable world of actual programming.
What's so cool about this is that it's not some brand new idea. This exact same evolution, from having to do everything manually at a low level to giving high-level abstract instructions, it's a classic story that's happened over and over in computer science. Just think about the jump from assembly language to something like C, or even SQL. With assembly, you are painstakingly telling the computer exactly how to move bits of data around. It's incredibly tedious. But with SQL, you just declare what you want. You say, give me these users, and the database engine figures out the best way to do it. It's a huge leap.
And that is exactly the kind of powerful abstraction DSPy is trying to bring to AI development. The whole point is to let you stop worrying about the low-level how, the exact phrasing of a prompt, and instead let you focus on the high-level what, the actual logic of your application.
Okay, so how does DSPy actually pull this off? Well, it all boils down to two really simple but incredibly powerful building blocks. First up, you've got the signature. The easiest way to think about this is like a function definition, but for an AI task. You just declare what the inputs are, what the outputs should be, and give it a short, simple instruction. It's just a clean way to define what you want to get done, totally separate from how the AI is going to do it.
So once you have that signature, the what, you pair it with a module. The module is the how. It's the actual strategy the language model will use to get the job done. Think of it as the engine that takes your instructions from the signature and makes it happen.
And DSPy comes with different kinds of modules for different jobs. You've got predict for simple one-shot answers. You've got chain of thought, which tells the model to reason step by step. And then you have things like react, which can build powerful agents that use external tools. The real magic here is that they're interchangeable. You can swap these strategies in and out without having to rewrite your entire program.
Okay, so you've laid out your workflow with signatures and modules. But wait a minute, where are the prompts? This is where it gets really cool. The DSP compiler finds the best ones for you, completely automatically. This is basically the automated replacement for all that painful manual tweaking we talked about. You just give the DSP optimizer your program, a handful of examples of good inputs and outputs, and a way to measure success. Then the compiler just goes to work, testing out all sorts of different prompts and examples to find the absolute best combination that gets you the highest score on your metric.
A really advanced optimizer, like one called MIPROV2, does this in a few clever stages. First, it just runs your program to find some successful examples to learn from. Then, it brainstorms a bunch of new potential instructions for each step. And finally, it intelligently searches through all the combinations of these new instructions and examples to find the absolute highest performing setup. Now, all of this sounds great in theory, but does it actually work in practice? Well, let's look at the numbers, because this whole programmatic approach can lead to some really dramatic and totally measurable improvements.
Let's take a look at a real-world example. Here we have a React agent, and its job is to answer complicated questions by searching through Wikipedia. So this isn't a simple task. It requires some serious multi-step reasoning.
And wow, the results are pretty striking. Before any optimization, the agent was only getting the right answer about 24% of the time. But after running it through the DSPy compiler with just a small set of training examples, that accuracy more than doubled to 51%. That's a huge jump in performance, and it was achieved completely automatically.
Here's another quick one for you. This time, it's a classification task. The goal is to use GPT-4o Mini to categorize different kinds of banking questions. So right out of the box, the model was doing okay, about 66% accuracy. But after DSP did its thing, that score jumped all the way to 87%. The system went from being kind of useful to being highly reliable. And again, this was all through that automated compilation process. Look, at the end of the day, this is about way more than just getting a higher score on some test. It's about bringing real, proven software engineering principles into the wild west of AI. What you get are systems that are more reliable because they're tuned on your actual data, code that's easier to maintain because it's broken into logical pieces, and programs that are way more portable because you can just recompile them for our brand new language model.
So this kind of leaves us with one big question. If a compiler can automatically find better prompts than a person can, does that mean prompt engineering is dead? Well, maybe not dead, but its role is definitely changing. It feels like we're moving away from being these low-level prompt whisperers and becoming more like high-level AI system architects, focusing on the program structure and the quality of our data and just letting the compiler handle the tedious stuff. And that, well, that feels like a pretty big step into the future.